welcome to Developer Testing, Theory and Concept. So what I'm talking about in this video is developer testing, which is distinctly different than other kinds of testing. For example, quality assurance testing or end user testing and that sort of thing. We're talking about the kind of testing that's done during the development process, before the developer turns their code over for others to test their code and long before it gets placed into the code base. So one of the things we want to understand about developer testing is this is your frontline testing. This is the first testing that gets done. And developers are notoriously bad at testing. And there's a reason for that. And it's not because they're not good at testing. It's not because necessarily they don't understand what testing is. It's because typically developers have too much information. The reason developers are bad at their own testing is because they look at their code from the inside. They know how it works. And because they know how it works, they make a lot of assumptions that another user might not make. So what we really want to do is we want to look at how do we guarantee that developer testing is the best that it can be, okay? And this is one of the most important tasks a developer can do. If you can't do this, you can't be a developer. It's simple as that. It's probably more important than the coding itself. It's better to produce something that has less features, but the features are correct, that has more features and the features don't work. Okay, so if it doesn't work, it doesn't count. And what that means is your testing must be comprehensive. So what we're looking at is how do we guarantee it can be comprehensive? And as we said at the beginning of this, this is theory and concept, okay, as opposed to practical application. So practical application would be something like unit testing, test-driven development, to be testing frameworks where we actually hands-on write the code to do the testing. But before you do that, you have to understand the theory and the concept behind the testing. Okay, so as I've said in other videos, and I'll say many, many times, theory without practice, worthless. Practice without theory, worthless. Okay, practice is getting something done, getting it out there, getting it working. But if you don't have a theoretical foundation for making things work, usually your work is pretty bad. It's usually not good, and it's definitely not as good as it could be. Theory is what polishes practice. And the reverse is also true. If your knowledge is 100% theoretical and you can't do it, you can't put it out there, well, what does it matter? It doesn't matter until someone comes along and actually does it. So if you want to be a good developer, if you want to be a true engineer, you need both. What we're going to talk about here is the beginning portion of that. How do we start? How do we think about the theory and the concept of testing? And once we have that in place, that leads us to practical application. So the practical application is guided by the theory and the concept. And you can't do it any other way. There isn't a way you can do testing or pretty much anything unless you know why. At least you can't do it well unless you know why you're doing it and what's the idea behind it. So let's start with a topic that probably most of you haven't heard of. It's very unusual to me that most software curriculums, most software training, whether it's a code school or whether it's a university, doesn't teach what I'm about to talk about. Also, experienced developers. I can walk up to 100 experienced developers with 5-10 years experience, and I can ask them what this is, and 99% of them will not know. They may know it inherently at that point, but they don't know it by name. And it's important you understand this by name, and you understand that it guides our testing. It guides most of the work that we do in software. It's a very simple mathematical principle. It's known as the fundamental counting principle. And it's as simple as it gets, but understanding this will be the foundation for proper comprehensive testing. Once you know this, you know how to test, and you know how to test thoroughly. Okay, and the fundamental counting principle it simply states if there are P ways to do things and Q ways to do something else, there are P times Q ways to do both things. Simple example, if you have 3 shirts and 4 pair of pants, how many possible outfits do you have? Well, simple, it's 3 times 4 is 12. Okay, so very simple, very straightforward. There's nothing more to think about when you're thinking about this. I'll give another example, but the idea is just very simple. We're talking about combinations of things. This is the foundation. This is the theoretical foundation for proper comprehensive testing. So get another example. If you had a 6-sided die and you also draw a card from a deck of 52 cards, how many outcomes do you have? Simple. 6 times 52 is 312. So what we're doing is we're looking at things and how many things could happen. That's the idea behind this. How many things could happen? Think about how that relates to testing. You need to know how many things could happen at least. so that you can cover them all in your testing. When you test something, if the first thing you do isn't this, then you're already on the wrong track. You're already doing something wrong. If you're just feeling your way through it, if you're just thinking your way through it and thinking about the number of things that could happen along the way as you code, I already know you're going to miss something. You're already doing something wrong. Now, this can be extended to many situations that have more than two choices. You can extend it to any number of situations. The idea is to be as simple. If there's P ways to do one thing, Q ways to do another thing, and R ways to do another thing, then you have P times Q times R ways to do all three things. So it seems like a really simple, basic idea. And you're probably sitting there thinking like, yeah, of course, like I knew that. But did you really apply this to your code? Do you really think about this consciously when you're testing, when you're doing code? Probably not. And that's probably why your testing doesn't work well. Okay, so let's look at something that's a very straightforward example. So we're gonna talk about proper testing, and I'm going to use a stack abstract data type. If you don't know what this is, I have another video on it. Abstract data types using the stack as an example. It's not very long. You want to go there, watch that first, understand this example first, then come back, and then this will make perfect sense. But I'm going to assume that you have seen that, or I'm assuming you already know what a stack is. So we're going to proceed from there with that assumption. So the stack that we're going to talk about, it's written here in C++, and it's an object, what we're seeing right now is a class, right, that can be instantiated into an object. It's very simple and very straightforward. So a stack is a very, very simple data structure that allows you to put things into it and pull things out of it, but in an ordered way. And the order is a FIFO queue, first in, last out. So it's a very straightforward data structure. Whatever goes into the stack and other things go in after it. If you want to pull something out, the last thing that went in is the first thing that comes out. Okay, and the first thing that went in is the last thing that comes out. So very straightforward data structure. And when we pull things out of the stack, we call it pop. When we look at what's on the top of the stack, we call it peek. When we want to put something in the stack, we call it push. And we want to test the stack to see if there's anything in it, we call that is empty. The stack itself, the physical structure of the stack, is represented by two attributes. A stack array, that is the stack size. Okay, up here we're just saying stack size is 10, and top, which points to the top of the stack. Again, if you need to know more details, go look at the video about abstract data types, data structures, and stacks, and this will make a lot more sense. We're going to proceed as if you know what this means. So how do we test the stack? We're building one. Okay, so we have a toy stack here. It's just an integer stack. And how do we test it? And I don't know how many times I talk to programmers. It doesn't matter if they're students. It doesn't matter if they're beginners out in industry. It doesn't matter if they're 10-year or even 20-year veterans. They really don't know how to test. Okay, testing is just horrible. Developers are notorious for how bad they test. And that's a thing. We joke about it, we talk about it, but there's a reason for it. And the reason for it is what I'm showing you right now. Proper testing must cover at least, okay, that word's at least, the minimum number of possible states times possible operations. We go back to the fundamental accounting principle. So let's look at our case here. What are the possible states our stack could be in? Okay, our stack could be empty. Okay, and we try to do an operation to get something from the stack. That's called underflow. So our stack could be empty and there's nothing there, and we try to get something from it and we can't. So that's a state. A state is underflow. The other state it could be in is overflow. So overflow means it's full. All right, you try and put something else onto it, you can't. It's overflow, right? And then we have a third state, which is neither of those two previous states. So we have to think of what are the possible states that are our object or our function or our class or our system or subsystem or anything. It doesn't matter what it is. It doesn't matter what it is. Our thing. We have to think of the number of states our thing can enter. Okay, in this case, our thing is a stack. It's a class that's going to be instantiated into a class object. And the three states are overflow, underflow, and neither underflow nor overflow. Okay, now what are the number of possible operations? Push, pop, peek, and is empty. Those are the only methods that we created. Those are the only things possible for the user to do with these things, so we know. So what does that mean? How many specific tests do we have to go through? Minimum 12. 3 times 4 is 12, okay? So if you're ever doing testing and you haven't just done what I did before you even begin coding, you're already on the wrong track. We need to know all of the things that can happen to our stack and all of the states it can be in or a thing, whatever that happens to be. And even though we're not talking specifically about things like unit testing, frameworks and things like that, that would be the pure practical application of this. You should see already this guides that practical application. So as soon as you start building your unit tests, how many do you need? Well, you need at least 12. You know that before you even start. You know you need at least 12. Okay, so let's move on to what does this mean? How do we do it? So what would you do to execute all of the proper tests you need on our stack? Okay, you would place the stack into each state and then execute every operation in that state. That's how we get our 3 times 4 is 12. So place the stack in underflow. Presumably it's in underflow the moment you create it. Okay, so you create it, you're creating it's going to be empty, right? More than likely. Execute everything possible in that state. Try and push in underflow. Can you do it? You should be able to do it. That's your test. You should be able to push because there's nothing in there. Of course, you'd be able to push. You should be able to pop, you should be able to not pop. If it's empty, you can't pop anything. You should not be able to peek anything. If your test is empty, it should come back true. The stack is empty. So what we do is we put the stack purposely in underflow and keep it there. Keep it in underflow and execute push, pop, peek, and is empty over and over and over again, multiple times. We'll talk about how many times in a moment, but just multiple times, okay? And you gotta make sure you're doing this correctly. If you do push to test push, it's no longer an underflow. So you got to pop as many times as necessary to counter the pushes so that you can also test pop, peek, and is empty. Okay, so you got to do this intelligently. Now we do the reverse. Place the stack in overflow. Do the same thing. Execute push, pop, peek is empty. Same consideration. If you do a pop, it takes it out of overflow, put it back into overflow so that you can continue testing over and over and over again. Make sure to do all operations multiple times in this state. Then we get to the final state, which is neither overflow nor underflow. So what does that mean? We're gonna push and pop the number of times necessary to get the stack so that top is in the middle somewhere. We don't care where. It's just neither underflow nor overflow, and do multiple operations multiple times in this state. And again, same thing. You have to pay attention to. Keep it in the state. Keep it in neither overflow nor underflow, and execute those operations. This is comprehensive. Okay, well, now we're still not done. This is minimum, but this is now tested every operation in every state. Okay, and every time you're coding anything, makes no difference what it is. If it's a single function, don't care. If it's a class, don't care. If it's a system or a subsystem, don't care. It's all the same. It's all the same thing. You list your states possible, list your operations possible, multiply them. That's your minimum number of tests. Now, I keep saying minimum. We'll get to that in a moment. Now, also, let's talk about how you should do testing. Testing is automated, okay? Don't use user input. This is usually a beginner thing. Most experienced programmers don't do this, okay? They don't do this because it's such a pain. They've learned not to do it. But beginners do this all the time, where the first thing they want to do when they want to test something is they write some type of input line so the user can type some input, then that whatever's taking in the data can test it, and they get some answer back. You can't do proper testing that way. It's not possible. Testing has to be automated. You need tests that are tens of thousands, hundreds of thousands of iterations. You cannot do proper testing with user input. Never do it. There's one exception. Like everything else, right? In programming, we always say, these are the rules. Always do this, never do this. And then they immediately follow that with, but here's the exception. Now, there's an exception to don't use user input. And the exception is, unless you're testing a user input system. If you're testing a user interface where a person is interacting with something, that's an appropriate place to use user input to test, because that's what you're testing. You're specifically testing the user's actions. So if that's involved, then of course you use user input, because that's what you're testing. Other than that, we never use user input, okay? Use defines and constants based on the object, function, or system being tested. And by that, I mean, you want your tests to be fully automated. Now, fully automated means they're going to run without user input. It also means when you make changes to your object, function, system, whatever, the tests don't need to be changed. That's the thing. Ask yourself that question. Whenever you write a test, look at that test and say, if I change the size of my object, if I change the way the system works, will my tests stay the same and still work and be what I want them to be? You can't always do that, but your goal is to get as close to that as possible. So in this case, what would that mean? So here's a simple example. If I'm going to test filling the stack and overflow, Okay, so we go back to our test. Which one am I doing here? I'm placing the stack in overflow, and then I'm executing push. Okay, so I'm doing one state, one operation in this example. But I want it to be so that it's always going to work. No matter what I do, it's always going to work. Okay, so how would I do that? So I'm going to start a loop. And what's my count going to be in my loop? Something I see beginners do all the time. They will start a loop. They go, oh, if I got to fill the stack, I'll just do I equals 0, I less than 10. They'll actually write 10 in there. I plus plus, because stack size is 10. They'll write the literal in there. We have another rule. Don't use literals. And here's an example why you don't use literals. If you look at the way that I built this test, it says I less than stack times multiplier. So stack size is 10. Multiplier, we're going to make that up. Okay, so multiplier is going to be like, let's make it 1.2. Okay, so those defines are going to be my header file somewhere. A header file in this language, right? It would be a constant in some other language, in with your code, not a header file. But in this language, those would be defines probably in a header file. And if I change them, I don't have to change my tests. Suppose you come back up here and you're writing your stack to be size 10, and then later you decide like, oh, I really need to be size 100. You change the define in one place. Your test does not need to change. Okay, don't use literals. Okay, so our test does not need to change. You want this to update automatically and not have to go back and find that place and test it again. The problem is chances are you're not going to remember, right? You're going to change your stack size. You're going to forget to change your test. And now it's an invalid test. It doesn't work anymore. Okay, but this way it always keeps up. So if my multiplier is 1.2 and my stack size is 10, what does that mean? It means I'm going to go 12 iterations. The stack size is only 10, so I've accomplished my goal. My goal was to fill the stack and test push, right? That was one state, one operation. Okay, and here's the code for one state, one operation. And it always works because I use defines, and it guarantees to go to overflow no matter where the stack was. It guarantees overflow because if stack size is 10 and multiplier is 1.2, then we're going to 12. So whether the stack was half full or empty makes no difference. It's going to go to overflow. It's going to push it past its limit, and it's going to see what happens. Right, and that's where we get our answer. So I'm just going to grab since this is an integer stack, I grab a random value, I push it onto the stack, and then I test it. Right, I report. No, sorry, the operation itself is the test, and then I report. If I was able to push, I say pushed. If it was not, I say error. Okay, now this is generic code for a concept. Let's make sure we understand that. It's generic code for a concept. This is the idea behind it. In real testing, once you transition to practical, you probably don't want output like this. You probably don't want a print statement. What you want is some kind of count that you can automatically compare. So I should know where my stack was. It was at top, wherever top was. I should push a certain number of times, and I should count them. I should count the number of times it succeeded and count the number of times it failed. All right, and then my test, what it would actually do in practice is it would report when that didn't work properly. Okay, so in that case, what we do is we would count. We'd say if top started at -1, let's say the stack was empty, and I pushed 12 times, what I should get is I should get 10 pushes, right? I should get 2 errors. I should count those. I should compare that to the size of the stack and where top was, and then I just report one thing. I report one thing: success, failure. Okay. Now, what I'm doing here in this example is I'm making it a little bit. It's conceptualized, right? You really shouldn't just say pushed and overflow error, because if you did, what's going to happen is you're going to get 20,000 lines of these outputs, and you have to read through them all to see where the mistake was. Now, obviously, this is conceptualized. I'm just trying to get an idea across. Once you transition from this idea to practice, then what you're doing is you're counting, comparing, and you're only reporting success and failure so that you know exactly where that happened, and then you can go back and find out, well, what was the mistake that caused a failure? Okay, so this is the idea, though. The idea is how do we test a state and an operation, and it's this right here. Okay, so also use random operations. So what I've said so far is test every state, right, and every operation in every state, right, and that's going to give us 12 things. And I give you an example of one state, one operation. You should be able to extrapolate from that and generalize it to a more practical case, right? And do that for every state, every operation. But we also want to beat up our systems as much as possible with random operations. You've got to think that like you're never going to cover it all. You're never. And the danger of the previous procedure, right, is it's very explicit. So I counted states, I counted operations, I multiplied them, I got a number, and I did that thing. But I'm human, and maybe I forgot a state. Maybe I forgot an operation. Maybe I wasn't aware of a state that it could enter. Okay, that happens in very complex systems, right? You think it could enter only 5 different states, but there's a 6th state that is probably an invalid state or a state you didn't want to have happen, but it's so complex that it could enter it and you didn't think of it. Okay, so we always need random operations too. The random operations kind of cover us, right? They cover if we made a mistake, we didn't think of something, we didn't think of some combination of things. So what do I do in this case to do random? Again, this is conceptualized. It'll be something like this. Okay, so what you're going to want to do is again use defines. Right? Notice I have a loop here that goes from stack size toward random multiplier. So what's that's going to be? Random multiplier is going to be a big number. Okay, something like 10,000, 100,000. It's relative to your stack size. Maybe you want to make random multiplier a function of your stack size or whatever it is, your object size, your array size, whatever it happens to be. It makes no difference. So random multiplier might be something like stack size times 1,000. That way, if stack size changed to 100, random multiplier changes relatively. If stack size changes to 1,000,000, random multiplier changes relatively. Okay, so it wants to be something like that where you don't have to think about it again. So in this case, let's just assume it's some big number, right? It's like 1,000 or 10,000, something like that. We want to execute these operations and we want them to be random, mostly random. There's a little bit of intelligence behind this too, but mostly random. So think about what we're doing here. We got push, pop, peek, and is empty. It's 4 states. If we have 4 states, we want at least 4 cases. I'm going to argue you want a little bit more than 4 cases. What you really want in this case, notice I have choices here, is a define. Okay, it's a constant or define. And in this case, I'm setting it to 6. And the reason I'm setting it to 6 is I actually want to do more than 4 things. I want to do 6 things because I want the operations that can alter the state to happen more. Okay. So that's another theoretical concept in testing. You want to make sure that you test the things that are dangerous more than you test the things that are not dangerous. Inherently, anything that alters data is dangerous. Anything that reads data is mostly not dangerous. Okay. So what I want to do in this case is, even though I only have 4 operations, what I want to do is I want to actually do push and pop twice as much as the other ones. Not in aggregate, but like conceptually twice as much as the other ones. So what I'm going to do is I'm going to give 6 states. I'm going to give 1 and 2 to push, 3 and 4 to pop, 5 to peek, 6 to is empty. And that's going to cause push and pop to happen more. And the reason again for that is those change the state. Okay, so in object-oriented terms, those are mutators, whereas peek and is empty are accessors. And we want to make sure that our mutators are tested way more, or in just general terms, anything that writes should be tested more than anything that reads. Because writes are dangerous, okay? And they change state. And that's what we want to do. That's what we're trying to accomplish. We want state to change as much as possible during these random operations because we want to cover as many cases as we can just to be thorough, but also in case we miss something, okay? So I didn't write the full code here. This is more of a concept. It's an idea. And then what you're going to do inside of each one of these cases is that's where you write your code. And inside those cases, you may have something more complicated there, right? You may call a function that does some type of automated pushing a certain number of times or guarantees like some states and some other states while also ensuring that random things happen, right? So you can make that more interesting where I have the comments here for push, pop, peek, and is empty. So random operations, tens of thousands, hundreds of thousands. I've never understood a lot of developers, whether they're beginning or expert, they never push it, right? It's a computer. It doesn't care. What's the difference between 100,000, a million, or 10 million times, like a second, right? So use it. Use the power of the computer and make your testing do hundreds of thousands of iterations in random states and random operations so that you can really be sure this thing is solid, okay? So what do we have here for a conclusion? Use the fundamental accounting principle to guide your testing. Again, this is all conceptual. In practice, what you're going to do is you're going to follow now a framework or a methodology of some type, like unit testing, it's a framework, or test-driven development, that's a methodology. In practice, you're going to follow one of these, but begin those with the fundamental accounting principle. First, count your things and count them properly. Then ensure you understand the combination of states and operations. And don't think to yourself, I'm going to give you a clue as to why developers are so bad at testing. Don't ever trick yourself into thinking as a developer, oh, well, I'm not going to test this state and operation combo, whatever it happens to be, because I know it can't enter it. Okay, that's why developers are so bad at testing. I've just summed up everything about why developers are so bad at testing, because you know too much. You know what your work is, and in your head, you have preconceived notions. You say to yourself, well, I have 3 states and I have 4 operations, but I know that the fourth operation doesn't ever get called in the third state, so I'm not going to test that. Okay, there, I've just summed up why developers are bad at testing. They presuppose that they know more than what the user is going to do or try. And then they say, well, that's not possible because that's the way I coded it to not be possible. And you screwed up. It is possible. And then the user does it and you fail to test it and your work fails. So you want to, when you're a developer, you want to blank your mind, right? Blank your mind and think to yourself, like, I know nothing about this thing. I don't have any preconceived notions. Use the fundamental accounting principle blindly. Okay, you gotta dumb down yourself so you're not the developer anymore. You're the user who has any idea what's going on. Okay, and you're going to do anything. So there's a saying in software engineering: you must always assume every user, and this includes other developers of your code, right? Other developers using your code. Somebody else takes your code, they want to enhance it, they want to expand it, they want to use it, whatever. It doesn't make a difference. It includes end users and other developers. Those are all called users, okay, of your code. And there's a saying: you must assume every user is both dumb and malicious. Both, right? They both have no idea what is going on. They have no idea how to use what you're giving them. And they're trying to break it on purpose. That's how you have to think. And the fundamental accounting principle is what leads you down that path properly. Just count. Don't think. Do the count, regardless of what you think can happen. Then beat it up randomly. Okay. If you begin with that concept, the rest is going to fall into place. Okay. So just use these concepts for the basis of your testing. All right, hopefully that gives you a good foundation to begin testing properly and expand your testing, and go back and take a look at some of your testing and see, did you really cover every case? Or when your testing failed, if you followed this, would it not have failed? All right, and I'm going to guess probably it wouldn't if you just follow these simple ideas.